and what is the reflection coefficient at any position on the transmission line. One of the special cases is when the position z equals to 0, you got 1 and 2. Those are very easy, right? But for these two, you use the formula. You use the equation, you write down just everything down. Okay. So, I'm trying to telling you that for the specific location for some position z, every position z, you will get different reflection coefficient, you will get different impedance, input impedance. Okay? It is a function of length or position, the reflection coefficient, and the input impedance is also a function of physical length or position. Okay? They are related to each other according to the equation you write down. They are Smith chart. Smith chart is a way you trying to draw gamma and z in. Okay? According to different ZL and Z0. How to use Smith chart? So I think most of you already took the EM class. You know something, but I try to help you to review. Okay. For this example, you guys already have a Smith chart, right? I just gave you a Smith chart. First of all, find out the ratio between ZL over Z0. What is ZL over Z0 equals to 2, right? It is a pure number, but it is possible if this is imaginary or it is a complex number. It's complex number, it's okay. You just try to find out the ratio between ZL and Z0. For this case, the ratio is 2. This is a normalized load impedance, normalized, because I divide by Z0, okay? So the number is 2. Okay, go see your Smith chart. Find out the 2 on this line on X. On X, you will find out, you will see that at the middle, it is 1, right? So there is a number around here. You see it is 2. Got it? Did you find 2? Okay. So, here is here. Okay? It is 2. So what is the load at that point? It is 2 multiplied by 50, so become back to 100, okay? Then you will have a Like, what is the next step we are going to do? Everyone, if any of you bring your compass and your Smith chart, next week you can get an extra point. Bring compass, 带圆规来，下个礼拜加分。Compass and the Smith chart, 1 point. If you remember, okay? Bring your compass. So, that's easy, right? It's happy class, right? Use your compass. Draw a circle from your ZL. So this is ZL. 2. Draw a circle, and the center is the middle. You can draw a circle, okay? So bring your compass. We will do more examples, and I will explain how to calculate Smith chart, okay? I'm trying to tell you how to use Smith chart at the beginning, and I try to use the equation to explain the details. But no matter what, maybe you forget what is the reason, but doesn't matter. The most important thing is you need to know how to use Smith chart. This is how to use Smith chart. Okay. Find out number 2 and draw a circle. Okay. Do you remember what we just derived? How long you will repeat? How long Smith chart you will repeat the same thing? How long?
Lambda.
Half wavelength. Half wavelength. Okay. So this circle means half wavelength. If you come back to here, it is half wavelength. Which means if you go to the half circle, this is a quarter wavelength. Okay? This is a quarter wavelength. So, what is this point? Can you try to find out on your Smith chart even you don't have compass? This is 2. What is this number?
0.5.
0.5. What does that mean? It means if my physical length of the transmission line is lambda over 4, your input impedance is 0.5 multiplied by the normalization number 50. Okay? So the input impedance is 50, so it is 25 ohm. Did you remember that what we just calculate for our impedance transformer if it is a quarter wavelength transmission line and your transmission line is 15 ohm? What is the input impedance? 25, right? Do you remember this case? We just say that. With your Smith chart, you can find out any input impedance anywhere, not only in a quarter wave transmission line. You can find out maybe 1/3, maybe 0.4 wavelengths. You just use this beautiful table. You can obtain any input impedance for the transmission line. But don't forget to multiply back your normalization impedance. Okay? So you got it? And there's more surprise, not only the input impedance. but also the reflection coefficient. The reflection coefficient, it is a function of exponential. There is the phase, right? Actually, the radius, the absolute value, the radius of this circle, the number of the radius, the value of the radius, 半径, okay, of this circle, it is the refraction coefficient. We get the absolute value. You can obtain these two simply, directly from your Smith chart. That's why it is important. There are, you can see these two equations are complicated, right? But with this Smith chart, you can directly get these numbers. Understand? Okay. Then you can see that something from this Smith chart. The radius never change. The phase is changed. The radius of this orange circle is the reflection coefficient, but the phase is changing. There's a 2 pi of if there is a different phase changing on it. Absolute value is keeping the same. When you calculate the return loss, the equation is minus 20 log reflection coefficient of your gamma, right? So your return loss is keeping the same on the same transmission line. That's why you are moving the position of your output impedance. Guys, okay? Okay. Understand? So how to do the calculation? Okay. If you want to find out what is the input impedance for the quarter transmission line, you find this point, right? But how about if the theta is 40 degrees? It is not 0.25 degree. It's not. It is if the theta, if it is changing to others, you will use something outside the table. Did you see there is a number. Did you see the outside? It is a wavelength on the left part. Did you see a wave? Write down wavelength toward generator and wavelength toward load, right? For the outside, it's from 0 to 0.25. So the half. Did you see that? The outside it is 0, and then there's a number 0.25 here. Okay, so this is a quarter wavelength from here to here. So if you want to do, those are just a mark for a position. If you want to know what is the length of maybe 0.3 lambda, what is the impedance after 0.3 lambda? You can find the number 0.25 here. At 0.25, this is 0.5, right? And also 0, right? you can see, yeah, it's 0.5. So you want to see 0.3 is 0.25 plus 0.3. You're supposed to get that at 0.55. It's somewhere here. It's 0.55, but you don't have 0.55. You have something, you minus 0.5. It's 0.05. Okay? Do you know how to use it? Those are the coordinates. The thing is, those are the coordinates to help you to find out the wavelengths and use your compass to find out where, and you should know where is your ZL, and this is Z in, the new Z in. Okay? And when your position Z equals to maybe 0. For this one, 0.3 lambda G L. If you understand, raise your hand. If you don't, I try to find another way to explain. Okay, you understand? No? Okay. How about you guys? No? Don't understand? Okay, still don't? You don't get it? Okay. Okay, go back to the easy part. Okay. First thing is, one circle means half wavelength. We don't have a question, right? So, the circle, that means you changing the position of your transmission line, okay? And the location of this point is the input impedance, okay? Do you guys understand? This is the input impedance, where it is. Because if this is 0.5, you multiply 0.5 to 50, you obtain 25. So this is the half wavelength case. But I want to tell you more that there are more than half wavelengths. You can change up. You can use the arbitrary wavelengths. You can change for all the case, right? So which means your circle, location of the circle is changing everywhere. You know, half wavelengths, they will repeat the same result. The thing is, you need to understand where your ZL is depending on the angle. The new angle, change this angle to a new angle. And this angle is the same as your beta L. Too complicated? Okay? No? How to find out your position of new input? How? It depends on your length of transmission line, how long it is. On this Smith chart, we only use how many wavelengths it is. Okay? You can see the outside of the circle, they write down the number 0 here, they write down the number 0.25 here, okay? And also, this is also 0.5. So one circle, it is 0.5, which is half wavelength. According to the number on the outside circle, you can understand what is the difference about the arc between your ZL to Z in? Okay, let me write down one more example to explain this case, and then maybe I will let you guys take a rest, and next week we continue, okay? I put some example here to make you guys think. You need take a rest, maybe too much. For this example, let's take another example, more complicated example. If ZL is 100 and the Z0 is 50, right? If the L is 0.3 wavelengths, okay? For this case, is more spatial, right? So, your Smith chart will start at 2 because 100 over 50 equals 2. Okay? This is normalized ZL. This is here. Okay? For 0.3 lambda, I try to use the compass to draw a circle. Here it is 2. I find the location of what is Z in. Z in at L equals to 0.3 lambda. Where is 0.3 lambda? You find here, you can see the location. What's that? 0.5, right? If you put 0.5 at 0.3, you can get 0.8, right? But you don't read 0.8 here. It is 0.5 or 0, right?
0.25. 0.25.
Here? Okay, yes, 0.25. And this is 0 and 0 and also 0.5, right? So it is supposed to be 0.55, but there is no 0.55. You should find something, it is 0.05 because now it is 0. So you find a line, you should also bring your ruler. Not only compass, you also need ruler. 带尺跟圆规都要。Okay, and your Smith chart, ruler, compass, and okay, you can get extra. And here, this point, it is new Z in at L equals to 0.3 lambda. Okay, read the number here. Multiply by 50. Okay, but so far you learn only the pure number. I told you the pure number is on this X, right? You know the number here. There are also number at in the up half and the down half. Those are the positive J and the negative J. You can read the number. Did you see the number in the inner circle? There are, maybe next time I will just use the symmetry. For this one, it is the wavelength, the outside circle. But the inner circle, you can see some number, like a 0 point from, I think it's a lot of number, right? The inner one, from the 0, 0.1, 0.2, 0.3 until 50 and a lot of number, right? Did you see that for the inner one, right? Okay, that is the imaginary part of Z in. So you find out new position. There are two values of this new Z in. For the first value, go back to the axis, you will see the real number of normalized real number, okay? It's a normalized. And also, there are some of that telling you what is a normalized part of the imaginary number, okay? Then you multiply 50 number back, you will get this. This one. Okay. This is an easy case, 100. For exam final, you will obtain more complicated number, maybe 77 plus J 30. So you need to find out this normalized number for this log first. And maybe this is 100. So your beginning is not here. Your ZL is 0.77 plus 0.3J. Can you find out this point on your Smith chart? It will be 0.77 will be in the left side, right? And the 0.3J is something up here. 0.3 or maybe here. Okay. Then you draw a circle and changing the length of the transmission line to another position and find out what is new input impedance. Okay, and also the reflection coefficient is here. How to find our reflection coefficient? Use your ruler to see what is the radius of the circle, and use. Did you see in the bottom there is a reflection coefficient? There is a ruler in the bottom. You can see reflection coefficient. You put the same radius on the ruler of the bottom and then check the reflection coefficient. Too much, huh? Okay. Okay, I think it's finished for today. I just try to